So students, open page 169, 189. So page 189 NCERT. The topic is acceleration due to gravity of the earth. So on page 186 we have studied two important results of the Newton's law of gravitation. First is this result, that the force of attraction between a hollow spherical shell of uniform density and point mass just situated outside is as if the entire mass of the shell is concentrated at the center of the shell. So if this hollow sphere, this is the center, its mass is m, and I have this point object. I want to find the gravitational force between these two. So I assume that the whole mass of this hollow spherical shell is concentrated at this center of mass. This is my mass. Now I know by gravitational law that the force of attraction will be G small m capital M divided by the distance between them. Okay. Second result. So these are the two results for two special cases: force of attraction between extended object and point mass, how we are going to take. So I told you that we can consider earth as we can divide the earth into concentric spherical shells and use this first result. Second result, the force of attraction due to the hollow spherical shell of uniform density on a point mass inside it is 0. So like I have this point mass. Now this point mass is inside this hollow spherical shell. So the force of attraction on this point mass is 0. Okay, because it is being pulled by all the points of the hollow spherical shell, and these forces will cancel out and the result will be 0 there. So there will be no force acting on the mass inside the spherical shell. Now let us read from page 189, acceleration due to gravity of the earth. The earth can be imagined so we can imagine the earth to be a sphere made of so this is our earth's surface. This is our earth's surface, and we imagine the earth to be a sphere which is made of large number of concentric spherical shell with the smallest one. So we are assuming that this our earth is made up of large number of concentric shells. Okay, like this, and the largest one is at the surface of the earth. A point outside the earth is obviously outside all the shells. So a point outside the earth's surface is obviously outside all the shells, and thus all the shells exert a gravitational force at the point just outside it, just as if their masses are concentrated at their common center. Okay, according to the result that we have just discussed. So this earth has, we assume it, consider the earth to be made up of concentric shells, and so and we have a point mass m which is over here, which is at a distance r from the center. So this is your center, and we have a mass m, suppose at this point, okay, inside the surface of the earth. So this distance is r. Okay, let us see what other so this is re is the radius of earth, this radius of earth. This d, this mass m is in a mine, you can say, which is located at a depth d. So we have dug this mine over here and put this mass at depth d, okay, below the surface of earth. And me is the, this me is the mass of the surface of earth, and this re is the radius of earth, okay. And what is this mr? Mr is the mass of this sphere, okay, mass of this sphere, right? So these are the variables that we have here. Now, so students, you have to read the NCERT line by line, okay, along with my notes. So after reading my, taking my class, you'll be able to read the NCERT books. You can read it simultaneously also. So the total mass of all the shells combined is just the mass of the earth. Hence, a point outside the earth, the gravitational force is just as if the entire mass, so if a point is there outside the earth, so, or outside a solid surface, outside even this surface, so like this surface we are taking, so both, so we assume that the whole mass of the earth is whole mass, this mr, mass of this sphere, whose radius is small r, so this mr is concentrated at the center of this sphere, okay, because we have placed the mass over here at the depth d below the earth's surface at this point. So obviously the the outer concentric shells will have no impact on this mass m, okay. So only this much sphere, the mass of this sphere, will have gravitational force on this mass m. These outer concentric shells, we have studied conclusion number 2, that the force of the gravitational force due to outer concentric shells will be 0, right? So the gravitational force, so we have divided this earth in 2 parts, you can say. So for a point inside the earth, it is divided in 2 parts. Come to page number 190. So again, consider the earth to be made up of concentric shells as before, and a point mass m situated at a distance r from the center. The point P lies outside the sphere of radius r. The shells of radius greater than r, these shells, okay, these shells, even the surface of the earth, okay, these shells whose radius is greater than r, for them the point P lies inside, and hence according to the result we have just studied, they exert no gravitational force on mass m kept at point P inside them. So now the shells with radius less than r, so these shells whose radius is less than r, they will for which the point P lies on the surface, this smaller sphere, these concentric circles exert a force on the mass m at P, as if its mass mr is concentrated at the center, okay. I hope you have understood this concept, students. Is this clear to everyone? Now, what is the mass of earth? Mass of earth is equals to, we know the mass of sphere is equals to 4 by 3. So mass of sphere is equals to 4 by 3 volume, sorry. So what is This we did yesterday also, students, if you remember. This concept we used yesterday also. Can any of you tell me what have we used yesterday? The concept something like here density is equals to mass upon volume. So like for a particular volume we find this mass. So yesterday what we did, some similar thing like this we did, remember? Yes. See, yesterday we did, when we were finding the gravitational force, this gravitational torque, means this was our rod L and this was our string attached to it, and we have the spheres over here, large spheres over here. So these are the small spheres and these are the large spheres, lead spheres these are, which have very high density. So they were, you know, this rod L was rotated a bit by angle theta, and this wire was twisted. So this wire was twisted, right? So this angle theta, so there were two forces acting on it. One was the gravitational force due to the spheres. So these two were equal and opposite forces over here. So this sphere was, so when these are two equal and opposite spheres, the resultant torque is given by, so this resultant due to this gravitational force is given by this length multiplied by one of the forces. So this F into L. So this is the magnitude of the gravitational torque. Now as this wire is twisted, we have the restoring force, and restoring force depends on theta. As this theta is increasing, it is just like spring force. Spring force is directly proportional to the displacement, and then we have spring constant. So here, just like this, we have tau. This restoring is tau theta, this restoring force. So here these two forces are equated. Restoring force, this is the restoring force, and this is the these are, both of them are not torques. Okay, so this is the torque due to gravitational force, and this is the torque, restoring torque. So FL is equals to tau theta. Now what is F? So F is equals to G M, the mass of big sphere and the mass of this small sphere, GMM, divided by the distance between them. So the distance between them was small d. So this d square into L. So this is F into L. So the force is, this much is the force. So that's equals to this. But where do we have the concept that I was discussing, that the mass with that concept? So this value, simply put it over here and we can find the value of from this equation we can find the value of G. This is what we did yesterday. Okay, so that concept, okay, we'll discuss later rest of the things. Let us come back to the topic. So density is equals to mass upon volume. Now what is the mass of the earth? So mass of the earth is equals to volume of so what is mass? Mass is equals to volume into density. So volume of earth into density of earth. So that is what the mass of earth is. So simply put, what is the volume of earth? So this is the volume and this is the density. So that's the mass of earth. So radius of earth and then this density. Okay, now what will be the mass of this sphere? Because only gravitational force on M due to this sphere. Okay, So radius is r. So here also the formula remains the same. This mass is equals to volume into density. So this mr is equals to volume of this sphere whose radius is small r into the density of earth. So that's just the same. So how much is this volume? This volume is 4 by 3 pi small r cube. So that's the volume. Now the density is rho. So 4 by 3 pi r cube into rho. Okay, so you can write it rho later or rho here, that's the same thing. Now we know this mass is concentrated at this point. So now let us take this sphere. So you have this sphere and mass is concentrated at this point O, and the radius is r, and you have placed the mass m at top of it, and the mass of this is 4 by 3 pi r cube. So what is the force, gravitational force acting on m? So the force on mass m at p has the magnitude F is equals to g m1 m2 by r square. So this is m1, this is m2, right? And just simply putting the value of this mr here. So this is your mr. So put this value over here. This is your mr. So you put the value of mr and you get this, and you simplify it. So now put this value of 4 by 3 means you have to bring here ME, RE, mass of the earth, radius of the earth. So what is this? You need to remove this density part. So 4 by 3 pi. So you have ME and you have MR. So what is ME upon MR? So ME upon MR is 4 by 3 pi and this small r cube into rho. So you can clearly see that 4 by 3 pi, 4 by 3 pi cancel, density cancel. So ME upon MR is equals to RE cube upon R cube. So 4 by 3 this 4 by 3 rho is ME upon MR. Sorry students, we need not to calculate ME upon RE. We have to, so this is MR we have inserted, so we can, this as equation 1, this as equation 2. So this we did from equation number 2. Okay, now this ME upon RE, so this is simply putting this value of rho from here. So rho is equals to you can see that this is or you can say 4 by 3 rho value you can find. So 4 by 3 rho, so this RE simply went to this side. So this is ME upon RE cube. Okay, so this value we just put over here in this part, and this part will become this. So this is using first this equation. So 4 by 3 rho, value of 4 by 3 rho. So 4 pi by 3 rho is equals to ME upon RE cube. Okay, now this r square and this r cube, so only one r will be left, which is over here. Now this is the force on mass m, but we have to calculate the gravity on the surface of earth. So now if m is the mass situated on the surface of earth, then this r, small r, this will become the radius of earth. So this r will be changed to radius of earth. So this r will be changed to radius of earth. Now when this will be changed to radius of earth, so one radius of earth means it will be cancelled out, and you will be left with GMME upon this r is changed by this RE, and this RE get cancelled with this one, and you will get r square. Okay, so here what you have done, F is equals to GMME. So r is replaced with RE because now you are on the surface of earth, so r is equals to RE, and then the gravitational force on mass m. So this will be RE upon RE cube. So this will be cancelled out and you get this value. Now we have the formula of force. So force is equals to, we know that this is the weight, same as the weight of the body. So F is equal to mg, and from here we get F is equals to this. So now we are going to equate both the value of forces. So what will be the value of g here? So this m gets cancelled out. So this g is equals to GME upon RE square. So students, this is the value of g. Okay. Now we know the value of g already, and we know the radius of earth that we did in by the parallax method in chapter 2, and this Cavendish found gravitational constant. So we know these two already, but we didn't know the value of g, and once we know the value of g, we have found the mass of the earth. So that is why some of the time, because this value of g, gravitational constant, helped in finding out the value of mass of the earth. So we sometimes we say that Cavendish weighed the earth, because Cavendish gave us the value of g and we found the mass of the earth using this formula. Okay, so pretty simple derivation, students, very simple. And now this value of g we will be using further. So now we will be finding acceleration due to gravity at a depth, at a height above, not at a depth but at a height above. So this is the height above the earth's surface. So consider point mass m at the height h above the earth's surface. So what will the magnitude of the force on this mass m, which is over here? So this is F is equals to g. So F is equals to g m1 m2 by r square. So write the standard formula, and your mass m1 is your mass of earth replaced with this. m2 is your mass of object, and what is this distance r? This distance r is between the two masses. So from the center of the mass you can take this distance. So what is this r? So r here is your this distance. This distance is your distance. So because whole mass of the earth is assumed to be concentrated, because it is divided into concentric spheres and their mass are concentrated at the center of the hollow spheres. So all their mass are concentrated over here. So here we have mass of earth. So we have these 2 points now, m and this me. So and this distance is h, and this distance is your radius of earth. So the total distance is re plus h. So we have replaced. So this is another important way, students. Write the standard formula and then simply put the values, replace them. So that's how we get the magnitude of force. And you can see clearly that this gravitational force is a function of h. So this is a function of h, means as you are changing the h, so it also means that h is the only variable. Okay, only variable in this formula. So when it is only variable in this formula, we write with this H. So the magnetic force only depends on H, because this G is constant, this mass of earth is constant, this mass of the object is constant, the radius of the earth is constant. So this is another important, students. We have used this with VH also, gravitational potential energy, when we were writing, and that was mgh. So there also m was constant, g was constant, so it was only depending on h. So similarly here also, so this is what is mean, that the gravitational force is a function of h here, and it only depends on h. Okay. Now the we know that F is equals to mg, and what will be G equals to F by m. So G is equals to F by m, and this is your equation 1. So put this value of Fh over here. Okay, so using first, so putting this value, this there was gm, this m was there, and there was m over here, so these two m's cancelled out, and we left with this. Now so that's the that's your result, students. Gme upon this. So what was G on the surface of earth? So G on the surface of earth was Gme upon Re square, right? This is we derived above. Now you can compare this Gme, this Gme, okay, but this is Re plus H, and this is only Re. So you have increased the denominator. So if you increase the denominator, this is inversely proportional to GH, so GH will decrease. So here so as you increase this H, so this acceleration due to gravity start decreasing. So suppose it is 9.8 meter per second square over here, so it will start decreasing 9.7, 9.6, 9.5, 9.4, 9.3, 9.2, and so on, and it will become 0. Okay, now let us find out when we are at very this height is too much, means too much means much greater than this height. We will be doing the case when this height is much greater than the radius of the earth. Okay, sorry, so we will be doing it later, but now we are doing the height to be much small, means this height is much lesser than the radius of earth, means this object is near to the radius of the earth. Okay, so this object we are considering is near to the surface of earth, so far away, going away and away, so it is diminishing. But what about when it is very near to the surface of earth, because that is what we take when we do this. And students, what is the this Re? So Re, which is radius of earth, let me tell you that radius of earth is equals to 6.37 into 10 raised to power 6 meters. Okay, so height, even if you take height 10 meter, this h is equals to 10 meters, still it is very less than this Re. So this is the case we are going to take, that height not too much away. Okay, you can say the height within so this is 6.37 into 10 raised to power 3 kilometer. So even if you take the height as 1 kilometer, still it is very less than 6.37 into 10 raised to power 3. Even if you add 1 kilometer to it, still the answer will be 6.37, because it is only up to 2 decimals. So still it will remain, still it is not impacting this. So that is why even 1 kilometer. So we want to take this case. Okay, so for that I have taken this is Re plus H whole square. So I have taken Re common from it. So Re I am taking common. So obviously I have taken RE common, so what will be inside? 1 upon RE, so I will be dividing with RE. This is another way you can understand it like this, and this is your H divided by RE. So I have taken the H common. So these two are equals. Multiply RE inside, you will get back this thing, okay? And that's equals to now RE square, and what you are left with inside. Okay, you have taken RE common, right? So you have to divide both with RE, right? You are taking RE common. So here you are left with 1. So 1 plus H upon RE, right? So, and the whole square. So students, see, if you multiply RE, you go back. RE, this you get RE plus, and RE cancel H. So you can always check that you are. So this you can write as RE square into 1 plus H upon RE square, right? So this is what I have written from here to here. So simply taken the RE common. So this is what we get, okay? And now this GH, this power 2, we have inserted this value of G first. So G is equals to GME upon RE square. So this value is your G, okay? This is your G. So simply putting this value, and then this value becomes your G, okay? And this is this power, when we write it in numerator, we write it as minus 2, okay? This exponential. So we have used as G is equals to this, because we want to compare here comparison of GH and G, okay? G at a height H and G. So now for height much less than this RE, see students, we use this kind of thing when we want to compare, and when one is very less, we take the common and we make 1 plus this binomial expansion, then we use. So this is another, one of the tools in physics that we use. So we will use it at many places in physics, okay? So because I want to means I know that this case I want to take H is much less than RE. So keeping this intention in mind, I took the RE common, so that it will be 1 upon RE. This will be very small number, because H is very small and RE is very large. So like it is something like 1 upon 1000. So 1 upon 1000 is very small. So 1 plus 1 upon 1000, you can do it with binomial expansion. So this is something like 1 plus R upon N, and you write it as 1 plus Rn, right? This is your binomial expansion. Yes, you know this, students? When this R is much less than 1, then we write this formula. We call it binomial expansion, okay? So here this H upon RE went this side, so H upon RE is much less than 1. So that is why we use this formula over here for the binomial expansion. So N is 2. So 1 minus 2 H. So what is value of N here? So N is your minus 2. So this 1 plus, and what is R here? R is H upon RE. So we get here that GH is equals to G into 1 plus H. So here we use the binomial expression. So thus you can see here that for small height, because we are taking this R value, so for small height this expression, this was for normal height, for any height. So this for height H, the means the value of G decreased by a factor this. So obviously this factor is less than 1, because H upon RE is very less than 1. So even if you multiply 2, still this number is very less than 1. So if this number is but you are subtracting out of 1 some number, so definitely this number is lesser than 1. So this total is less than 1, because you are subtracting 1 you are subtracting 2h upon re, however small it is, but still the value will be lesser than 1. This whole value will be lesser than 1. So you are getting gh equals to g into any value lesser, like 0. Even if it is 0.998, still multiplying with this, you will get this value lesser than g. So gh is lesser than g. So g decreases by this factor. Okay, by this factor g is decreased. So see, this is another important tool, how to write the increase or decrease by the factor. So if this number will be was greater than 1, then we'll write here that g increases by this factor. If this was greater than 1, if this number is smaller than 1, so you multiply number smaller than 1, it will decrease that number. If you multiply number greater than 1, then it will increase that number. Okay, now so now mass is at a depth d. So this is your surface of earth, mass is at depth d. So your point mass is over here. So here you have your point mass. Okay, now the g, we have to find the g at the depth d. So attrition due to gravity at the depth d below the surface of earth, and in this case only the smaller sphere, you know, will contribute to small g. So the radius of, what will the radius of this smaller sphere? This is the radius of earth, and this is your d. So what we are left with? So this is re minus d. So this is the radius of this inner sphere, re minus d. So only this will contribute to the g. Outer shells, gravitational force due to these outer shells will be 0, no impact on here. Okay, so this is the mass, and this distance is re minus d. Okay, now so mass of the sphere definitely depends on the cube of the radius. Density is equals to mass upon volume, and mass is equals to density into volume, and mass is equals to rho into volume is 4 by 3 pi r cube. So definitely mass is directly proportional to the cube. So mass of a sphere is proportional to the cube of its radius. So ms, which is the mass of the smaller sphere, so this is the mass of the smaller sphere. This who will this is the mass of the smaller sphere we are taking, and ms mass of the earth. So what will the mass of the sphere, and this ratio ms upon me. So definitely this will have this rho 4 by 3 r. These things are common, they will be cancelled out, and we'll only left with r cube. So their radius is, so what is the radius of small sphere? That is re minus d. So cube of it divided by this re cube, radius of earth. Okay, so this is the ratio. We need this ratio. Okay, I was about to calculating it earlier, but that was not required over here. It is required here. So the force due to smaller sphere of this radius is just if as the entire mass of the smaller sphere is concentrated at the center. So this is your mass m now, and this is your mass of the smaller sphere concentrated at the center, and the distance between them is re minus d. So now g is equals to gravitational force is equals to gravitational constant into m1 m2 upon r square. So here this is the formula. So fd will become, so this g is the constant. So what is m1? M1 is your you can take this as mass of the smaller sphere, this sphere, and m2 is your mass of the object that you have put point mass, you can say, and this r is your re minus d. Re minus d whole square. So this is your equation 8.17, this equation. Okay. Now substituting the value of ms from here. So what's the value of ms? Me will go this side. Okay. So put this value over here. So this you can write as equation number 1, and here you are using equation 1. Okay. Here you have used gravitational law to write this equation. So you'll get this. So putting this value Re minus d. So this, if you put this value over here, the value of ms, what do you get? So this Fd will be equals to g into Re minus d whole cube upon into me upon Re cube, right? This is the value of ms. Okay. Obviously ms we need to remove because this d is varying, so we don't know the mass of the sphere, of course, and it also varies with depth. Okay. So but mass of the earth and mass of the and radius of the earth, these are standard quantities. So obviously we want to write out this force in these standard quantities into, so I have put the value of ms over here. So so this ms is this value, so g and this ms, and then into m, and divided by Re minus d whole square. Okay. So here what gets cancelled? This is cube, so this is square, so this square will, and we are only left with Re minus d, so we are left with only one, this, and then this Re cube, yes, this Re cube divided by Re cube, and then this G m e into m. So this is the thing, G m e into m written over here. So that's the same thing. Okay. And this Fd, and hence the acceleration due to gravity. Now you know F is equals to Fd is equals to F is equals to m into G. Yes. So that's the. So similarly here, like earlier we used G is equals to F upon M, and put this value of F over here. So if you put this value of F over here, so GD equals to this, and this you are dividing with M. So this is what you are doing. You are simply dividing this FD divided by M. So only this M will cancel out. So this m will cancel out. Okay, and you are left with Gme upon Re cube into Re minus d. Okay. Now what is the value of G? G equals to Gme upon Re square. So Gme upon Re square. So you have R cube here. So 1 Re will left. Okay. So this replaced with this, and 1 Re square is there. So 1 Re will left here. So this is Re minus d. And further you can write it as GD. This of course you are finding GD. So at depth. So again you can see that this G acceleration due to gravity is a function of depth. So as d, and only function of depth. So as d is increasing or decreasing, so it will impact the value of G. So here this is equals to, now this is 1 minus d upon this. So again this number is again this number is again less than 1. So again less than 1 number you are multiplying, so again this G will decrease, right? So again the same concept, that because this number is less than 1. Okay, so GD is decreasing by the factor this. So as we go below the surface of Earth, the acceleration due to gravity decreases by a factor this. So we have studied that about the acceleration due to Earth's gravity is that it is maximum on the surface and it is decreasing when you go up or down. When you are going down, it is decreasing by this factor, and when you are going up, it is decreasing with this factor. So these are the factors by which it is increasing or decreasing. So these are the two ultimate formulas, because you just need to remember 1 minus 2h upon re and 1 minus 2d upon re. I'm multiplying them with 9.8, that's value of g. So students, that's all for today. So we have done the acceleration due to gravity at the surface, at the height h above, and at the depth below. Thank you so much for being with me.